Hello, today I'm going to talk to you about isotopes and average atomic mass. So just starting off with a review, this is the atomic symbol that we've already learned to write. Just a reminder that this is the one or two letter code for the element. For magnesium, it's M and a lowercase g. The number here is the number of protons. So for any time we're doing magnesium, it's always going to have 12 protons. So this is also the atomic number. And then the number up here is the mass number for this particular isotope of this element. All right. So an isotope is a version of a particular element that has a specific mass. So isotopes are atoms of the same element that have different masses. So if we wanted to write that in terms of different symbols, magnesium, which we were just looking at, has 3 different isotopes. It has magnesium 24, 25, and 26, right? And the reason that those isotopes are different is because there's a different number of neutrons in each of those different versions of this magnesium. Okay, so to write the symbol for each of those, we would write the magnesium symbol, the 12, because magnesium always has 12 protons, and then the number up here is going to be the mass. And if the mass is 24, we already know the protons is 12, so that means the neutrons must also be 12. And because we have a neutral element here, our electrons are also 12. Right? If we want to do the symbol for magnesium 25, the only thing that changes in the symbol is the number up here, because this is the mass number, right? So protons is still 12, electrons is still 12, because it's a neutral atom. The thing that has changed is the number of neutrons. So because this has a mass of 25, there must be 13 neutrons in this atom. Right? And then the last one is magnesium 26. So again, the only thing that changes is the number up here. Protons is still 12, electrons is still 12 because it's neutral, and then our neutrons, since it got one heavier, we must have one additional neutron, so we must have 14 neutrons in this atom of magnesium. All right, so because we have different isotopes that have different masses, right, that means that if we were to take a sample of magnesium, then some of the atoms would have a mass of 24, some of 25, and some of 26. So to find what the average mass would be for that, we need to do a weighted average, all right? So the average atomic mass is like if you take a whole bunch of atoms of the same element, and you have all the different isotopes mixed in there. If you were to take out like 100 of them, what would be the average mass of those atoms? Okay, so we're going to learn how to calculate that today, and I'm going to start with an analogy that's just a weighted average of something very simple. In this case, it's bowling balls. So let's say that we have 10 bowling balls, 5 of them are 8 pounds, and 5 are 14. Okay, so half our balls are 8 and half are 14, so our average mass is going to be halfway between those two, okay? But the way we would calculate that in terms of a weighted average would be to take the ratio. So this could be a fraction or it could be a percentage put into a decimal form. So if this was a percent, it would be 0.5, okay, which is 50%. All right, so that times the mass of that particular isotope or that particular bowling ball in this case, then the fraction that are the other mass, all right, and then we add those together. So half of 8 is 4, half of 14 is 7, so our average atomic mass, or our average mass for bowling balls in this case, would be 11 pounds. Okay? You could, in this case, also just do the average of 8 and 14, and that would also give you 11. But that only works if you have an equal number of both different masses. Okay? So let's say instead we have instead of 5 14-pound balls, we actually have 20. All right? So now our average mass is going to be heavier because we have more of the heavy bowling balls. All right, so how would we do that calculation? So now if we have 20 that are 14 pounds and we still have our 5 that are 8 pounds, our total number of balls is now 25. 5 of them are still 8 pounds, so the fraction that are 8 pounds is going to be 5 over 25. And the fraction that are 14 pounds is going to be 20 over 25. All right, so if we do that math, 5 over 25 times 8 would give us 1.6. 20 over 25 times 14 would give us 11.2, and we add those together and we get 12.8. All right, so you notice the average mass is always going to be between the two masses that we have. So no matter how many of each we have, our average is always going to be between 8 and 14. All right, and then whichever one we have more of, in this case we had more of the 14-pound balls, our mass is going to be closer to 14 than it was to 8. Here we had an equal number, so it's going to be right in the middle. All right, so now let's take this example to actual isotopes. So when we look at the periodic table, if you remember, I told you to ignore the numbers below the element symbols, okay, because they're decimals. They're not whole numbers, and that's because those are the average atomic masses, okay? So far we've been just writing mass number as a whole number because we've been adding protons and neutrons, right? So that's how you would do it for one single atom. But if we have a collection of atoms that don't all have the same masses because they're different isotopes, then we wouldn't get a whole number, okay? So the equation that we are going to use, all right, if we have the percent abundance of each of our 3 isotopes of magnesium, the equation we'll use is that the average atomic mass is the sum of the product of the percent abundance and the mass. All right, and this percent abundance could also be a fraction, like it was in our previous problem. Okay, so if magnesium-24 is 78.7% of our sample, that's 0.787, right? And then the mass is 24. Then we'll add to that the percent abundance for magnesium-25, all right? And then we'll add to that the percent abundance for magnesium-26. All right, so if we do all that math out, we get, you know, this product is 18.89, this one is 2.53, and this one is 2.90. Add them together, and we get 24.3. All right, this is in atomic mass units. I didn't write that there, but that's the units that we're working with. All right, and if you look at your periodic table for magnesium, you'll see that the mass is 24.305. Okay, so this is a little bit more precise because our masses here were only to the nearest whole number, but we should get a number that's close to what's on the periodic table. Because of that, I'm always going to require that you show your work so that I know what your thought process was and that you're not just taking the number from the periodic table. All right, so now we'll do some practice and you'll all become masters at this.